Welcome to this tutorial on analyzing FPOD data. My name is Nick Tregenza, and we're going to look at this quite difficult subject of species interactions and interactions with sonars, pingers, the noise of moving sand, etc., and address the question, can we analyze these independently? Um, Obviously, ideally, they would be completely independent. But actually, um, that's a difficult thing to achieve. And in medical diagnosis, back in the 17th century, physicians came up with this term pathognomonic, which meant a feature that pointed to the disease that the unfortunate patient had to have. And these pathognomonic features were extremely valuable because they basically gave you the answer regardless of anything else. They were completely independent. And back in the days when I was a family doctor, I used to see Koplik spots in the mouth of children with measles, and that was a pathognomonic feature, which has largely disappeared since measles immunization came along. But anyway, we're supposed to be talking about FPOD data. So this this subject was sparked off by an interesting paper in JASA Express Letters this month. Dolphin and porpoise detections by the FPOD are not independent. Implications for sympatric species monitoring, which raises these important questions and refers to another paper on which I'm one of the two authors, along with Julia Ivanchikova. That's validation of the FPOD, a fully automated cetacean monitoring system. So perhaps we could start by looking at some real FPOD data. So here's a file. It's about 111 days of data. You can see down here, click shown. It's got 205 million clicks in the raw data, and 2.5 million have been found to be in trains. So here we've got open 3 copies of the raw data, the FP1, and 2 copies of the FP3. And you can see that we've got dolphins, or that's the other cetacean group, in orange. Some porpoises, that's the narrowband high frequency group over here. Some sonars in this maroon color, and some where no species has been allocated. This is an important category. They're called unclassed, and they will contain some of each of these, but didn't make the grade for being definite enough to get classified as being a porpoise, for example. So the essential problem is that dolphins, some dolphins at least, can produce narrowband high frequency click trains, and they do this sometimes. Some species more than others. In data I've seen, Tursiops oduncus in Australia is particularly liable to sound like a narrowband high frequency species. So if you find a click that looks like a good narrowband high frequency click, you can't really say which species category it belongs to. So you might sort of really tighten the criteria up and say it's got to be in this length range, bandwidth range, etc., etc. And you get better and better at excluding the dolphin versions of a narrowband high frequency click. But you've done that at the expense of losing a lot of your detections of porpoises. because when their clicks are weak, because they're only just sticking up above the background noise, they appear to be shorter than normal. They appear to be broader in bandwidth, etc., etc. So, generally speaking, you can't distinguish those two categories just on a single click. Um, Sonars, they're pretty distinctive, or they can be. So, at one time I thought if you said if it's got more than 100 cycles in it, it must be a sonar. So we could just check that. If we set here a filter, files and filters on clicks, and say the number of cycles has got to be at least 100, and we look at, say, 100 milliseconds, and we do show from start, show next screen. So it whizzes along until it gets to this point here. And if I now hit F4 to ignore all filters and zoom in a bit, we can see what we've got. So we've got number of cycles at the top there. So these are very definite porpoise click trains. But some of them here are going, well over 80 clicks. This one's over 120, not clicks, 120 cycles or waves, if you like, within particular clicks in the series. And this click's got over 120 cycles. Doesn't mean the animal actually produced 120 cycles. It could be that a number have been joined together by multipath propagation, which I won't explore in detail here. But so that hopefully pathognomonic, absolutely indicative feature for sonars, that doesn't work either. There really aren't any that you can be completely sure about. So the classifier has to cope with this. If it's only hearing things that sound like porpoises, it's happy. It puts everything into porpoises. But if there's a dolphin present, then it's kind of not so sure. And that creates a bias against identifying one of the cetacean classes when the other one is present, or either of the cetacean classes when a sonar is present. So this is a kind of tough and distressing problem which we'd much rather not have to deal with. But say you want to investigate it. Is this interaction giving you problems? There is a fairly simple kind of numerical approach that you could apply to this file. I'll just redraw the whole file, but I won't redraw these three copies of the FP1 file because it's a bit slow with 200 million clicks each. Okay, so I'm seeing almost nothing there, so I must have set a filter in here. Did I do that? Clear all? Yeah, I set click cycles to be 120. Okay, show from start. So now we've got our dolphin, sorry, our porpoise detections up there. So there's not a huge number. There's only 77,000 clicks there. So before embarking on a study on this file of how big this interaction is, I can do what is a kind of primitive power analysis, really. I can go to the let's do it for sonars first. I can go to the analysis page, and file 4 is an FP3, and I can get the figures for sonars. So it says sonars have got 1565 dpm in this file. So I'm going to put these into a spreadsheet, and guess what? Here's one I prepared earlier, and there is your number of sonars, your number of NBHF, your number of dolphins, and the total number of minutes in the file. So for each of these categories, I can calculate their rate per minute. That's the probability of a minute being positive for that species. So then if I wanted to study, shall we say, do dolphins interact with sonars, I can come up with a prediction of how many minutes will have both if they're randomly distributed. And this is quite a simple formula. It's, yeah, we can now see it there. So it's the number of minutes in the file multiplied by the fraction that will have dolphins, which is pretty small, multiply the fraction which will have sonars, and it comes out at 79 minutes would have both if they weren't interacting. Well, that's kind of nice. We could then test and see if the actual figure is lower than that. And you could do it for obviously any of those other interactions. But before we do that, we could just check out by getting some graphs up what we might expect. So in the graphs here, I've put file 5, which is the number of clicks. File 4 is the kilohertz. Maybe I'll make that. Yeah, okay, we'll leave it like that. So we'll do that for sonars. So that's going rather slowly. I'm just going to stop it a minute. Yeah, it's wading through those FP1 files. So this is sonars. Here's the frequencies. You can see there's quite a lot of sonars reported as being up there around 120 kilohertz, which is troublesome because they might get misclassified as porpoises. Then there's a lot of sonars at 50 kilohertz, probably another bunch at 100. And they're occurring mainly in the daytime. So there's some eager fishermen are getting up at 5 in the morning. This pod is just off a rocky coast with a sandy seabed and near to a very small fishing port, harbour on the north coast of Cornwall in the south coast of England. So that's the distribution of boat sonars. So we'll just get the distribution of dolphins, and I'll just tell it to omit the FP1 files when it does these graphs. Okay, so the frequency distribution of dolphins is very different. There's no peak at 50. There's one a bit lower, and there's one up here. But the DL distribution is quiet in the day. It's kind of almost the inverse of the sonars. So actually, we'll get a lot less interactions than we would have expected. And that's not necessarily anything to do with the classifiers, but it could be a real interaction. It could be that dolphins hate boat sonars and don't like coming in there in the day when there's a lot of boat sonars. So I just mentioned that because this is quite a tough issue to analyze. Anyway, we're going to plow on regardless and look at how you might do this. Say you want to look at the interaction between dolphins and um, porpoises. So we'll just graph the porpoise detections here. So their frequency distribution is kind of what we expect. They seem to be like a bit more there in the day at this site. Is that because they don't like the dolphins, or they do like the boat sonars, or they like some fish that's easier to find in the day, etc. But of course, if there is an interaction, one of the effects, and there definitely is, if the classifier is troubled by saying, I'm not absolutely sure which category to put this in, it's going to put them in unclassed. So if we want to find out um, really what's happening, we're going to have to look at what's in unclassed. Okay, unclassed has clearly got stuff in it that isn't porpoises, and really what we want to find at the moment is the porpoises that are in unclassed. So we can set some filters here. I mean, what I'm heading towards is we're going to validate these by looking at them by eye, and I'm trying to reduce the size of the workload we have to do that. So we'll only look at unclassed at trains that are, well, it'll be actually about 110 kilohertz from the graph we saw earlier of what porpoises look like. And I didn't show you graphs of the mean number of cycles in a click, but basically it's higher for porpoises than it is for dolphins. So if we set that at 3, we don't exclude many porpoises, but we do exclude quite a lot of dolphins. If we do graph now, we've lost that big lump of dolphins that were in unclassed there. Oh, okay, just so we're now just showing unclassed, but they're looking kind of a bit similar, at least, to the porpoises. So what we're going to do now is go through this file, finding a sample of minutes that that have got porpoises or possible porpoises, and we're going to check out whether they've also got, first of all, whether it was porpoises, and secondly, does it have dolphins and does it have sonars? So to do that, we're going to go to the filters and files page and set validation sampling points. It's offering us find 100 of them. Doesn't like that. No open FP3 selected for action. Okay, so we can do that. Select this file for action. That's the right click pop-up menu. Set validation sampling points. Okay, so it's found 100 sampling points set in the whole of that file, and we can move from one to the next with Control and S. And we actually want to see everything now, so we can bring those back in. Control and S. So here's the first one. Okay. So it had something in there which it thought was a porpoise. I mean, or it was in that it was unclassed, but rather like a porpoise. So I'm just going to I'm just shaping up the graphs here to be useful. Okay, so what this looks like here is dolphins, and there's nothing there that really looks like a porpoise. So if we do Control and S, we move to the second of these points. Oh, I should have said what we can do is we go to results. We've got this list now, and we put no HP on that one. So this was the next one. So in clicks per second down here, we're seeing this flat line going through, and that is absolutely diagnostic of sonars. It's perhaps not quite diagnostic, but you can see there's a sonar which is at porpoise frequencies up there around 120 kilohertz. And unlike proper porpoises, it's almost continuous, and so this one's actually a sonar. So so this is no HP again. It's sonar. So that was probably unclassified. We can find that out by if we take that off. There was nothing there. So the classifier didn't say there was a porpoise there, but it did find something unclassed. This is okay. This is another sonar. It's got that very strong line going through clicks per second. This one, it looks like good porpoises here. So we've got they're in the right frequency band. They're showing nice features of the sound beam of the porpoise sweeping across the hydrophone, and you get these changes in amplitude as the center of the beam is closer to the hydrophone. So that one is good. I won't actually annotate these, but you can see how you do it. Okay, that one's going to be another sonar. That's another sonar, and another sonar. So this one is a sonar. We can see that line going through at porpoise frequencies. It's actually got other bursts of noise there. So what I'm doing here really is essentially sort of basic validation techniques. And here we've got a fairly straight line in clicks per second, but it's at quite a high rate. And to assess this, and it's also sort of broken up in a way sonars generally aren't, because sonars, they're highly directional, but they're pointing straight at the bottom. And what the pod hears is echoes that have come back up off the bottom, hit the sea surface, come down and hit the pod. So they're now scattered over a very wide area, and they tend to persist all the way through. These sampling points, they are kind of random, and when I did this before, it came up very early on with one that did actually have porpoises and dolphins in the same minute. But you could see that the dolphins were at very low frequencies and very distant. And as they got closer, you got more and more high frequencies. Anyway, this is how you go about it. So if you want to do a study on these interactions, you're going to have to find your files, check whether they are likely to give you or potentially able to give you enough interactions in the way I've just demonstrated. And then you have to go through like this, doing the validation. And the second paper that I listed earlier has got quite a lot of information about how you do that validation. And one of the things I've not focused on much here is getting the evolution of an encounter. So I'll actually just make this this one here show us the NBHF index. Okay, maybe that I'll make it just show us number of cycles. I want to get something that's so at this point we're getting good detections. If I look earlier by pushing the mouse wheel away from me, we'll probably see that these fizzle out. Yeah, so now we're not really seeing any at all. And then moving back, that's moving forwards in time. We start getting some of them and they get more and more. And then we come to the detection we had. And then typically they fizzle out fairly quickly. Yeah, and that's gone again. So this animal is kind of, or maybe more than one animal, heading towards the pod, looking around a bit this way and that. But eventually it moves past the pod and it disappears more quickly because you can't hear it. Not much sound comes out backwards. So you tend to get this ramp up and then a rapid fall off in the detections, the amplitude of the sounds picked up from either the dolphin or the dolphin group or the porpoises. Okay, that's quite a hard task. That's advanced FPOD or acoustic data analysis. If we wanted to do pingers, it presents some somewhat different problems, and I will have a look at those because they're kind of, you know, we're very happy to help with any of these analysis problems if you get them, and we've been posed. I'll just clear all that with how to analyze data on pinger studies. So I'm just going to find a pinger file. Okay, so I just loaded a file from a pinger trial using a comment file. Comment files you can save anywhere you like. So I obviously saved one just here when I was looking at this file. So you right click and you get save comment file. You click on that. You can give it any crazy name you like, preferably something very informative. Um, and then you can use it to reopen that file and go back to exactly where you were. And in this case, I saved it because here we had a banana pinger pinging away and um, a porpoise that was doing some feeding buzzes. So these are typical porpoise click trains up here, um, and here's a feeding buzz, and there's another one, and so on. And these things which are showing up in the FP1, these are pings from a banana pinger. So I'll just zoom out a bit further. So you can see that their spacing varies from about 4 seconds up to about 12 seconds. The frequency content varies from ping to ping. They randomize the content of the sound within each ping to minimize habituation. Just occasionally, these get pulled out as click trains, and from some other pingers, that happens much more often. So you want to study the interaction here, but because these clicks are very long, that makes the classifier think there's a sonar around, and it could bias it against detecting porpoises. So that would be really bad news, because when the pinger was running, the classifier might be showing less porpoises than it should. So the way you can get around this, well, first of all, if you're analyzing this, you want to know when the pinger's running. So if we do, we weren't displaying the FP1 down there, we'll do that. Show from start. Okay, so in this second panel up here, which is showing us the mixture of frequencies, you can see the pinger switching on and off. When the pinger's on, there's a lot in these kind of colors here, and when it's off, there isn't. So we'll graph that and see if that, oh, I told it not to graph the FP1, so we'll do that again. Okay, so this is the pinger is in here, and it's producing long clicks. So if I want to find when the pinger is on, I can look for periods when there are clicks between, say, 60 and 75 or 80 kilohertz that are long. So we'll go to filters, clear all view filters. These have to be click filters because they're going to operate in the FP1 file. And we'll ask for the click cycles to be more than, say, 20. Okay, now we'll do show from start. So this is looking dramatically different. Basically, in the FP1 file, it's just showing us when the pinger is on, which is exactly what we wanted it to do. So there it's got a bit of an outlier, and here. Anyway, we'll kind of stick with these filters for a moment. And what we'll do is we'll go to export. We'll ask it to export the number of clicks, say in an hour, from file 1. It's going to go in results. That's clear. Okay. And we'll export from file 1. Okay, so just to remind myself, what we're doing is we're trying to establish when the pinger is actually running. So we'll cut that to the clipboard. We'll go over to our spreadsheet and we'll drop it in there, and we'll graph the number of clicks. per minute. And we'll modify the axis here so that the maximum is, say, just 500 clicks on the scale. And so we've got a few things popping up in between here, but maybe if we put a line in at 50, that clicks. So we're going to look at how many hours have got more than 50 clicks. And that's going to tell us when the ping is on or off very nicely. It'll basically be replicating that graph we saw. Okay, so we're kind of making progress here. We've got out our pinger data there. Now we want to study porpoises. So we need click trains so that we don't get noise. We don't need high species confidence. And this low quality isn't saying the species classification is low quality. But again, we want to get porpoises that got pushed into unclassed because of the interaction with sonars. So yeah, we've cleared everything. What we're going to do is we'll ask for trains that are 110 to 150 kilohertz have got at least 3 cycles, mean of 3 cycles in each click in that train. We'll just do show from start to see what it's looking like. Okay, that's looking good. Obviously, we need to scale that down. I'll just hit F6 a few times. Okay, so over here we're seeing a bunch of click trains that are all unclassed, and I'm a bit puzzled by that. So I'm just going to zoom in on that and see what those were. So you can see the pinger firing away there. They do look to be at the right frequencies. But when we scale this up, we can see that actually what we've got here is a boat sonar that's intruding on this file, and that's very characteristic of a boat sonar. There aren't sort of a lot of breaks like you'd get from porpoises. So, okay, yeah. So that's a sonar that is going on for quite a while there. We could just look at the characteristic of these trains. I mean, they're getting quite a lot of cycles there. What we could do in our filters here is we've got the mean number of cycles from 3 to 255. If we picked just porpoises and we did an analysis, we will get a readout of the number of cycles. Okay, so it's looking like that. Occasionally it's up high here. We could just chop off longer long cycles with a lot of longer clicks, or we could go through and we've got to bring the unclassed in again. And we could knock out these trains. So we could say remove all cetacean species this minute. That's not going to do it. We could set train species to sonar. Oh, that was train species. Really, we want send train to trash. Okay, let's mark all trains in this minute. Okay. So we're marking the bad stuff now. And we can then when we come to do the final analysis, we can exclude all marked trains. Okay, so this is fairly difficult for this pinger study because it's got boat sonars that are coming in at porpoise frequencies, and the classifier wasn't claiming that they were porpoises, but we were admitting unclassed trains in order to get around any possible bias from the classifier. So we've probably got the same kind of thing going on here. Yeah. Oh, I think that was the same one actually. Okay, so that way you're going to end up when you look at your data, you'll exclude marked trains, and you'll be able to analyze the data having got round any bias that the classifier might have had. After you've done that, it's quite easy and quite quick to repeat it without going through this very thoroughgoing method and see if your results are significantly different. You may find that actually all that work didn't make a lot of difference, but at least you checked out the possibility that this bias issue was going to make a lot of difference. Okay, so what are the implications of this for studies other than these ones where you're actually studying interactions? If you were studying, say, a population trend, in a way, you wouldn't have to worry about your porpoises suffering from some interactions, provided the other things stayed the same. And you know what the other things are. They're primarily boat sonars and dolphins. But if they have changed a lot, you have to think about, well, could that be affecting the way the classifier is working? And the other paper, yes, this one that Julia Vanchikova and I written actually has the first ever, I think, estimator for how much you get species group A from species group B and vice versa. And that actually is really the way forwards in developing unbiased classifiers. The other paper which alerted people quite rightly to this problem tried to deal with it by using these options in the click train detection. So you can tell the KERNO-F classifier to behave as if there are no dolphins, or no porpoises or whatever. So this isn't running classifiers independently. What it's doing, say you're in a river, you know you've got no NBHF species. If you tell the KERNO-F classifier that in advance, it doesn't worry about that possibility, as it were, and it moves the dividing line. And if there are also no sonars, now it will perform extremely well and it'll put everything in dolphins. Um, and you can obviously figure out how this works. So if it's legitimate, but when you put your pointer over there, a message appears at the top up here, which tells you this increases the sensitivity of dolphin detection slightly, provided NBHF species are really absent. There's another thing that is useful to know, which is classification warnings. Are our files still open? Yeah, we've got the pinger file still open. We'll just see what it said for file 4. Excess slow dolphin trains equals risk of sonar errors. So that banana pinger file, it had a problem with sonars, and it has kind of flagged that up for dolphins. It didn't see it very often for porpoises. And if I go back to the original file we were looking at, which will have been in Britain cat size. Okay, here we are. Filters and files. That one's got the same problem, and it also says the pod is often far from vertical, which was true because it was affected by a lot of very rough weather there. Yeah, so these warnings are quite useful actually, and if you've got several file warnings, that's just the total number, then you really have to validate the whole file. Okay, so we have actually gone through an awful lot of stuff. So I hope you've survived. Thank you for surviving. And these are difficult problems, and if you're working on one, we're always very happy at Chelonia to look at your data, give you guidance on at least what we think might be a good way of going with it. And I hope that was useful. Okay, thanks.